very good morning and welcome to this course on the foundations of continuum mechanics. Today we will be talking about the Cauchy stress formula. So let us get started. The topics for today's lecture are as follows. First, we'll talk about a property of the traction vector that we discussed last time. Then we will move to the derivation of the Cauchy stress formula. That's one of the most important formulas in this course. We will learn how the state of stress can be developed using the Cauchy stress formula, and then we'll use this to define the Cauchy stress tensor. That is going to be a very important quantity in this course. So in the previous lecture, we discussed about the traction or the traction vector. So we assumed a body and a point P inside the body, and we created an imaginary slice in the body passing through the point P, which split the body again imaginarily into parts 1 and 2. So this was the cutting plane. Then we analyzed just the part 1. So the first part was drawn like this. The cutting plane was characterized using a normal vector n hat, and we discussed that this results in a traction vector at the point P, and the traction vector need not be in the n hat direction. So it can be in some other direction as I've shown here. And the traction vector is a special kind of vector because we have a superscript n hat here. This is due to the fact that if I change my cutting plane, that is, I decided to slice the body in a different way, still passing through the point P, then the traction vector would be different. So we were talking about the first part only, but there's also a second part, and we can draw the free body diagram of the second part as well. So let's do that. So this is part 2. Still we have the point P, and the normal in this case, we'll call this n1 hat because that's a different vector, and then this may result in a traction which we'll call as T with the superscript n1 hat. So the question for today is that how are these quantities Tn hat and T1 n1 hat related? Are they related? And if yes, then how? Well, the Newton's third law states that the force applied by part 1 on part 2 is equal and opposite to the force applied by part 2 on part 1. So we're happy about the fact that the forces are the same and opposite. But does that hold true for this special vector that is a traction vector as well? Let us see. So let's apply Newton's second law. First, we'll apply that to part 1. So Newton's second law states that the net force acting on a body, or the net external force acting on a body, is equal to its mass times acceleration, or we can also say that it's equal to the rate of change of its linear momentum. So we'll use the second form, that is, the net external force acting on part 1 is equal to the rate of change of its linear momentum. So let's write that down. So we discussed that we can split the forces into two types. One is the surface forces and the other is the body forces. So let's take the surface forces first. So gamma 1 is the surface area or the bounding surface area of the first body, or the part 1 of the body. Then we have the traction vector times d gamma, because traction vector is the force per unit area. So we have to multiply that by the area to get the force. Plus, now we'll talk about the body force acting on the first part. So that's integral over the volume omega 1, which is the volume of part 1 of the body, times rho b times d omega. So rho times b is the body force per unit volume, and that's multiplied by the volume d omega, and we integrate that over the complete volume of part 1. So this is the net external force, and this has to be equal to the rate of change of its linear momentum. So that's d by dt of the linear momentum. So the linear momentum can be written as, so we take a small mass dm, that is rho times d omega, and we multiply that by the velocity vector, that's v, and this is integrated over the volume omega 1. So this we'll call A, because we'll be needing this equation again. And similarly, I write the Newton's second law for part 2 of the body, and this we will call B. So just for clarification, in the figure that we have here, this area, which is this one, we had called this gamma star as in the last lecture. So we'll call this gamma star, and we are calling gamma 1 as the area of this part 1. So which is the complete area that includes gamma star as well, because gamma 1 is the bounding area for part 1. Similarly, gamma 2 is the bounding area for part 2, and this area is still gamma star, because that is just the opposite of the cutting plane. So with this in mind, I can write that gamma 1 intersection gamma 2 is gamma star, because gamma star is the only area that's common between the bounding areas of part 1 and part 2. And if I take the union of these two, gamma 1 and gamma 2, I have to subtract a gamma star from this, and that gives me the gamma, which is basically the bounding surface area of the actual body. So we'll call this as gamma, which is the bounding surface area for the complete full body. Right, so now that we have written the Newton's second law for parts 1 and 2, let us also write this for the whole body, and we'll call this C. And just to relate the volumes, I can write omega 1 union omega 2 as the complete volume omega. And of course, these are volumes, so the intersection between omega 1 and omega 2, the null set phi. So what we do now is we simply add equations A and B. So let's look at them again, and we'll add them. So this results in the following equation, where we write the integral over the bounding area of part 1. We'll split that into an integral over gamma 1 minus gamma star and a gamma star. Remember, part 1 has some portion from the overall body, and it also has the gamma star contained in it, because we had hypothetically sliced to create the imaginary part 1 body. And then we take from equation number B, we take gamma 2 minus gamma star integral over the area, and then we have a gamma star integral coming from part 2. Now the integral may not be the same, it's just that this is integral over gamma star for part 2. And then we have volume integrals, so I'll write them as omega 1 and omega 2, and this is equal to d by dt of the volume integral that we had in equation A and the d by dt of the volume integral that we had in equation B. So let's call this equation D. And similarly, just to represent them in a similar fashion, I write equation C as follows. So this becomes an integral, and I split the overall bounding area, that's gamma for the whole body, into two parts. One's gamma 1 minus gamma star, and the other is gamma 2 minus gamma star. and then we have an integral over the complete omega, and that's equal to d by dt over the complete omega, and let's call this equation E. So now what we'll do is now we don't need to have A, B, C, all we need is D and E for the discussion now, and we'll now subtract equation number E from equation number D, and let's see what happens. So we have a gamma 1 minus gamma star integral, and we have a gamma 2 minus gamma star, and we have this and this, so they cancel out. And then we have an omega integral here, which basically is the sum of omega 1 and omega 2 integrals on the left hand side. So these cancel as well. And if you look at the right hand side, we have the integral over the complete omega in equation E, and in equation D we have integrals over omega 1 and omega 2, which add to give the integral over the omega. So all we are left with is just two terms, that is this one and this one. But remember, the first one is coming from part 1 and the second one is coming from part 2. They're not exactly the same because of the differences in the direction and the traction vectors acting on them. So let's write what's remaining now. So this is integral over gamma star, the traction vector t n hat d gamma, that's coming from part 1, and from part 2 we have integral over the same area, but this time the traction vector is called t1 as we had done in the figure. Let me quickly go up and have a look. So you can see that in this green color here, we have written the traction vector as T1 with the superscript N1 hat. So we'll use these symbols. This becomes T1 superscript N1 hat times D gamma, and that's a 0. So now we are getting somewhere, because the aim was to relate these quantities, that is Tn hat and T1 N1 hat, and we have an equation which has these terms. So let's proceed now. We also know that the vector n hat is simply the negative of the vector n1 hat. Let's go up and have a look again in the figure. So we can see that they're the same planes, except that the outward normals are in the opposite directions. So the blue vector, that's n hat, is simply the opposite of this n1 hat. So with this, we have integral over gamma star, the sum of t n hat and t1 minus n hat times d gamma, and that's a 0. So this means that this quantity times the area, when you add this for all the infinitesimal areas in gamma star to make the complete gamma star, this is a 0. But we also know that the choice of the actual body, the whole body that we're talking about, this was ours. I mean, this could actually be a subset of the actual body that we were talking about. Even then, the discussion holds. So what it means is that the choice of gamma star for the integral was arbitrary. So if the gamma star in the integral over an area is arbitrary, so what that means is that the quantity, that is the integrand, has to be identically 0 everywhere on gamma star. So we can write that Tn hat is the negative of T1 minus n hat. So as we said, since the integral holds for any subset of the body and actually any cutting plane as well, so the integrand has to be identically 0. So we get this condition here. And in this condition, actually we have T and T1, but we sometimes write the traction vector in part 2 also using the vector t. So what differentiates the two is the unit normal n hat in one case and minus n hat in the other case. So it's clear that if you're writing t for minus n hat, that's a traction vector acting on the part 2 of the body. So this can be stated in words that tractions on paths 1 and 2 are equal and opposite. So this is an important relation and we must remember this. Now let us move to the second part of the discussion today, which is about the derivation of the Cauchy stress formula. So let's talk about the motivation of the Cauchy stress formula first. In the last lecture, we talked about the state of stress. We mentioned that the state of stress is basically an array or a list of the vectors n hat and the corresponding traction vectors t n hat. So what that means is if you have point P and you decide to create a cut, an imaginary cut, then the traction vector, that's t, where n hat is the unit normal to the cut direction, the traction vector t in this case is t n hat. Of course, if I change my choice of cutting plane, that is I change my n hat, my traction vectors will change. And we said that it's important to have a list of all these n hats versus traction vectors because this information helps us with material design. So we have lots of these vectors and the corresponding traction vectors to them. The question is how many n hats are possible here? Well, the answer is infinite because my choice of cutting plane is a continuous choice. So I can rotate my cutting plane or n hat and that will give me a continuous variation of n hat. So I'll have infinite amount of information here. So the question is how do we define a state of stress then? Do we have to perform infinite measurements in an experiment and tabulate all the infinites n hats versus the traction vectors corresponding to those n hats? And the answer is no. We have a good news. So the good news is that we can create a state of stress using a finite amount of information, despite the fact that there are infinite n hat choices available for us. And for that, we'll start the discussion by drawing three mutually perpendicular cutting planes. So let's do that. So this is the point P. And rather than having an arbitrary cutting plane, we choose the cutting planes in such a way so that they coincide with the coordinate planes. So this is the plane that has a unit normal in the even hat direction. Then we can have a plane which has a unit normal in the E2 hat direction. So that's this green plane. And then we can have a plane which has a unit normal in the E3 hat direction, which we'll draw in blue color like this. And it has a unit normal in the E3 hat direction. So I'll also write the x1, x2 and x3 directions like this. So these red, green and blue are actually cutting planes through the point P. So we decide to slice or imaginarily cut the body using these three planes, and we'll try to link the traction vectors that we get on these three mutually perpendicular planes to the traction vector on an arbitrary n hat plane. So P, x1, x2, x3 is our coordinate axis. And we will have three traction vectors on these three planes. I'll just draw one of these. So let's say for the red plane, that is with a normal in E1 hat direction, we'll have a traction vector, something like this, on the E1 hat direction. And I can draw traction vectors for E2 and E3 planes as well, but that will mess up the figure. So I'll assume that you can imagine the traction vectors on E2 hat plane and E3 hat plane. So let's write these three traction vectors. So first we have T on E1 hat, which can be written using its three components like this. And then we can also write the traction vectors T on E2 plane and E3 planes like this. So you can see that we've written the three traction vectors on three mutually perpendicular cutting planes. Using the initial notation, we can write it in a very compact form, which is T, and then you can see the index of the superscript matches with the index on the right hand side of the superscript. So this is EI equals T of EI, but then we have 1 1, 2 2 and 3 3. So this becomes subscript j times vector EJ. So this is a compact way, and remember this is all at point P. We're talking about traction vectors at point P. We must remember that. Now our hope is that we'll want to express a traction vector on some arbitrary n hat cutting plane as some function of the traction vectors on these three cutting planes, that is T on E1, T on E2 and T on E3. So now we'll see how we can do this. And by the way, if we can do this, which I'll tell you we can, because that's the reason we are doing this exercise, is that our state of stress will then only require us to specify these information. That is, we have to specify only three normal n hats, and then for the traction vectors, we'll require T on E1, T on E2 and T on E3. And using this, we'll be able to find a general T vector on n hat plane using this information. So we will be able to calculate the state of stress using this finite compact information. So we'll now derive the relationship, that is this functional relationship here. So what we want is, we want to relate the traction vector on some arbitrary n hat plane with the traction vectors on three mutually perpendicular planes. So the approach we take is as follows, that first we have to look for a shape inside the body which has sides which coincide with these four planes. So one of them is the n hat plane and the other three are the three coordinate planes. And then we will figure out how to relate the traction vectors on these four planes using the Newton's second law. So let's start the derivation. So this is our coordinate axis centered around the point P. And then what we do is, we form a tetrahedron using points A, B and C. So we'll join A, B and C. And the tetrahedron is basically having four faces. One of these is the face ABC, and the other three are faces APB, BPC, and CPA. So you can see that the three faces which have P in common are coinciding with the three coordinate planes. And we choose the points ABC in such a way so that the normal to this plane ABC coincides with the plane n hat that we are interested in terms of the cutting plane. So we'll specify that. So this is our n hat, and the traction vector on the plane ABC will have some arbitrary direction. We'll call this T n hat. And this tetrahedron that we have here is a small portion of the actual body that is under consideration. And this is around point P because we're interested in finding the relationship between T n hat and the other three T's at the point P. So in the approach, we have the shape now. And the next thing is to be able to write the Newton's second law. We will assume for this derivation that the body is under equilibrium. That is, the net external force acting on the body is 0. So let us say that the area of the face ABC is given as delta gamma, and then the area of the other three planes that coincide with the coordinate planes will be as follows. So let's take the first one as BPC, that is, let me highlight that is this plane. This will become the projection of the area ABC on the coordinate plane. So this basically becomes delta gamma times the cosine of the angle between APB and the plane BPC. So this becomes simply the n1 component because that is a projection of n hat on the x1 plane. Similarly, the area of the plane APC is the projection of ABC on the coordinate plane which is perpendicular to x2, which is this one. So this becomes delta gamma times n2. And similarly, the third one, the remaining one is APB, which is delta gamma times n3. And now with this knowledge, I'll now apply the equilibrium equation. So when we apply the equilibrium condition, we'll have a sum of all the external forces equal to 0 on this tetrahedron, and the external forces can be written as a sum of surface forces and the sum of body forces. So for the surface force, we will write the integral, closed integral over the complete surface area gamma times the traction vector T of n hat times d gamma plus integral over the volume omega times the body force times the density times d omega, that is equal to 0 for this tetrahedron. Now this tetrahedron was a small portion of the body. We written that. So what we'll do is, instead of writing the integral, we'll assume that the traction vector on any given surface does not change too much because it's a small body to start with. So we'll write this integral, the closed integral over gamma, as the sum of four integrals over the four surfaces of the tetrahedron. So this becomes T n hat times delta gamma, that is for surface ABC, I'm assuming that the traction vector does not change on the surface ABC. So I'll write star, which denotes an average over the complete surface. And also in this case, the traction vector on surface ABC does not pass through point P. But ultimately our aim is to write the traction vector through a cutting plane with a direction n hat passing through point P. So that is the reason we put a star here, which denotes the fact that this is an average plus this is not passing through point P for this plane. But later what we'll do is we'll take the limiting case where the tetrahedron collapses to the point P, and in that case the area ABC will all collapse to the point P. But for now we are putting a star here for clarification. So I'll go back to the figure and I'll put a star here to denote the fact that this traction vector is an average value over the plane, and it could also be slightly away from the point P. Right, so let's go back and let's write the sum. And then we have, let's say we have the plane BPC, which is the orange one here. So for that, this becomes the traction vector. Now what is the outward unit normal, which is in this case a minus E1 hat, because we talk about the enclosing surface to the volume, in this case the tetrahedron. So the enclosing surface orange one will have an outward normal which is minus E1 hat. Put a star again here because we have removed the integral, so we are assuming that this is an average value over the complete area times the area of BPC, which is delta gamma times N1. And now I'll complete this pattern. And then we have the body force, which again we'll assume that the body force vector B is an average over the complete volume. So we write plus the body force vector with a star on the top left, which basically means it's an average. So we have removed the integral, times rho times delta omega, that's a 0. So let me specify that this star denotes an average value over the surface, hence integral is removed. So we'll use the condition that the traction vector on a plane minus E j hat is negative of the traction vector on the plane E j hat. This we had shown in the beginning of the lecture, and we'll use the initial notation. So the above equation now will become T with the subscript I, because now we use an initial notation, times n hat times delta gamma minus, put a star here again, T of Ej hat. So you can see that I've used this relation here. So we get a minus here, and then this gets multiplied with an Nj times delta gamma plus the body force vector Bi times rho times delta omega is a 0. So now we use the relation that the volume of a tetrahedron is 1/3 times h times delta gamma, where h here is the perpendicular distance between the point P and the plane ABC. So if I use this condition, then my equation simplifies further because we'll be able to get rid of the delta gamma. So this becomes so now is where we take the limit of small h tending to 0. So we take the limit h tend to 0, which basically means that the tetrahedron collapses to the point P, because if H tends to 0, the tetrahedron, the volume of the tetrahedron tends to 0. So the above equation now becomes T with an n hat I. So now you can see I've removed the star now, because now the traction actually approaches the traction at the point P, the local value, not the average value, minus Ti over Ej Nj plus, now since small h is tending to 0, so this term becomes 0, and therefore this is equal to 0, or I can write an equal to here. So this is the expression we were waiting for, because now we have expressed the traction vector on any arbitrary cutting plane n hat in terms of the traction vectors on three mutually perpendicular cutting planes. Now there's something interesting happening here, that this quantity here, which is a traction vector on a coordinate plane EJ as a cutting plane, has two free indices. I'll write it down. It has two free indices. So this allows me to define a tensor, a second order tensor sigma ji, as T subscript I Ej. So I'll call it define. And if I write this in the matrix notation, this is what we get. The sigma matrix on the left hand side, and then we'll have the 9 components on the right hand side. So the first component becomes, now we've written sigma, where j is the row number, and the row number coincides with the superscript ej hat. So for the first row, we have T E1 hat, and then the column number is 1. Second one becomes T2 E1 hat, and the third one becomes T3 E1 hat. Then the second row of sigma, where the first index again represents the row number, of course, in a tensor, and this coincides with the index of the Ej hat on the top. So this becomes T E2, and the other terms are like this. So with this definition of sigma, I can write this relationship that we had here using sigma on the right. So this becomes Ti n hat is sigma ji and j. I'll box it because this is the Cauchy stress formula. So this is the stress formula, the Cauchy stress formula we've been waiting for in this lecture. So let's look at this sigma tensor again. So this sigma tensor has 3 rows, where the first row is the traction vector on the E1 plane. These are the 3 components of that. The second row is the traction vector on the E2 plane, and the third row is the traction vector on the E3 plane. So that's what we wanted. we wanted to be able to write the traction vector on any arbitrary plane n hat using the three traction vectors on three mutually perpendicular cutting planes, and we have been able to do that. So that's a success. In fact, this tensor sigma, which comprises the three traction vectors, is called the Cauchy stress tensor. So the Cauchy stress tensor is nothing but the three traction vectors as the three rows of it on three mutually perpendicular cutting planes. So in the symbolic notation, I can write the Cauchy stress formula as the traction vector on any arbitrary cutting plane n hat as the dot product. Now you can see that the indices are like this. So the dot will look like this, n dotted with the Cauchy stress tensor sigma. So this brings us to the end of this lecture, where we were successfully able to derive the Cauchy stress formula and define the Cauchy stress tensor, which is one of the most important physical quantities in this course. Now please take a note of it that although we did this derivation by assuming the body to be in equilibrium, that is the net external force acting on the body was 0, but it can also be derived for a body which is accelerating. So in that case, you'll have to take the net external force as the rate of change of its linear momentum. But we did for an equilibrium condition for simplicity today. So now that we have defined the Cauchy stress tensor, we will spend some time later this week discussing more about this tensor and understanding how to use this quantity. So thank you very much, and I'll see you next time.